This lecture considers the numerical integration of second-order ordinary differential equations. This is commonly done in structural mechanics for transient forced response. You might wonder, why do structures people do that instead of working with first-order ordinary differential equations as some other fields such as flight mechanics or fluid mechanics do? The answer is that when we already have perhaps 500,000 equations that are second-order differential equations, we really don't want to turn that into 1,000,000 first-order differential equations. After all, storage costs run 2/3 of the total cost of the process, and just holding that many coefficients in a computer is an expensive process, more so even than the actual floating point operations that occur. So structural mechanics people like to deal directly with the second order ordinary differential equations and not reduce those down to first order. I'll start with an overview, mention some of the integration ideas, then we'll soon concentrate on Newmark integration, which is the one that was developed in the civil engineering community by Newmark at Illinois, but has found a lot of application in other mechanical fields. I'll do an example of a small pair of spring suspended masses, and we'll put a transient load on it and show the resultant motion. Then we have about 3 homework problems that are worked out in the problem session. Numerical integration is sometimes called step-by-step integration or marching in time. It's useful for transient forced response of systems, and this can also be due to initial conditions that have been put on the body and then started in motion. The integration can either use physical coordinates or modal coordinates. We're going to use physical coordinates in our examples today, but the integration using modal coordinates is very similar. One difference is that it's a little more difficult to apply initial conditions that are non-homogeneous to the modal coordinates. You have to figure that out and how that's interpreted in terms of the modal coordinates themselves. There are implicit and explicit schemes. Implicit schemes are a little more sophisticated and a little more work because they require inversion of the mechanical impedance matrix. Explicit schemes only look back in time and are never forced to invert the mechanical impedance. Let me sketch the time history of a typical system to show what happens when you do a numerical integration. Generally, you know the system behavior for a certain set of points, shown here as a system at rest. Then you divide the time axis into these evenly spaced increments, perhaps called delta t in size. Then, using the differential equation shown here, plus an approximation for the acceleration and velocity in terms of past values, we're able to construct a new solution here and then connect our displacement field to that. At some subsequent time, we get another solution, perhaps another here, and so on. And by so doing, we're able to map out some sort of transient behavior. Let me show a flow chart that maps out some of the kinds of vibration that we might study. Free vibrations would be those used in normal mode calculations. Force vibrations would be those that are governed by external live loads. We'd also consider initial conditions that force the system to be a force type of problem. A steady type of motion can result. This could be due to harmonic loads where the system vibrates harmonically, or periodic where you could use a Fourier analysis. Those kinds of problems don't lend themselves well to numerical integration because they are irregular in nature, and they can be studied by analytical methods. Transient problems are those where there are impulsive forces or strange things happening where the load changes character. These can be solved either by direct integration or by modal methods. The modal area we're not interested in yet, but would have a similar set of subcases under it as are shown here under direct integration. So just consider that the modal methods would have a similar set of possibilities. Direct integration will deal with the physical nodal coordinates. The older explicit methods were the ones that have been used for some centuries actually. They're differencing methods. You can use central differencing, back differencing, forward differencing, and there are many tricks of the trade in the explicit solvers. The implicit methods are what we are really interested in today in structures, and the Newmark Beta Method is probably the leader. I know that Hubolt did a lot of work on stationary random response. Wilson's done a lot of work on earthquakes, and so there are other people who've had other versions of implicit solvers, and they're somewhat closely related, really. They're not that different from each other in philosophy. But we'll study the Newmark one at length. Explicit integration methods are favored in many technical fields. This method leads to simpler programming. It can use less computer time in certain situations, such as nonlinear problems, because it avoids inverting the mechanical impedance matrix, which might be changing in time and have to be redone many times in an implicit method. But explicit methods use data from the past n steps in time, and then they project forward to the current time. I've mentioned nonlinear cases. When I was younger and worked with a professor named Ivor McIver here at Michigan on automobile crashing, we used explicit integration, and it was possible to write rather compact Fortran programs to do that. A problem with explicit methods, though, is that they can become unstable. That is, you can have numerically induced oscillations or even a divergent type of motion. To get proper stability, you have to take many small steps. And then the accuracy of the method is related to that step size, so the common way in explicit methods then is just to take smaller and smaller step sizes until you get the accuracy that you need. This method does give you a filtering action because with a rather large time step you don't observe the system very often, and therefore you lose high frequency content. That makes this a low pass filter. Examples might include 5-point integration, which I used earlier in my career on separation of a missile nose cone from the basic missile body. That was at Bendix Aerospace Systems. And then common central difference methods, which might use, let's say, 3 points in time, the current time, a future point, and a past point. Now let's equally discuss the implicit methods of numerical integration. These use information from the past time and the equation of motion at the present time, so you couple more tightly the system of equations, thereby requiring that inversion. These are a little tougher to program, therefore. You can make these unconditionally stable regardless of step size. Now that is interesting. You can take really large time steps. Unfortunately, when you do that, you then have a stronger filtering action. Again, you have a low pass behavior, but it happens in a way that is smooth, and it tends to only attenuate the predicted response. You don't get a case where the calculated response goes berserk and oscillates or diverges. So the penalty for taking really large step sizes is that you smooth out the response and lose the high frequency character. The examples, as before, are Newmark, Wilson, and Hubolt, and we're very interested in the Newmark method. Newmark integration is often called the Newmark Beta Method because of a parameter beta that's used in the method. It's an implicit method, and it can be made unconditionally stable by adjusting parameters gamma and beta that naturally occur. You can put on both accuracy and stability conditions in determining gamma and beta, and we'll show how that's done. There are three vector equations that are considered in setting up the Newmark Beta method. The first is the equation of motion at the current time, shown here. I'll use red symbols for the unknown quantities and assume that these are the ones that are to be found at the current time. We have the equation of motion, which involves n equations in 3n unknowns, but now we need two more relations to get a set of 3n unknowns in 3n equations. One of them is to interpolate velocity, as shown here. And in the figure at the right, I've put the unknown quantities as red stars, and those are to be determined by relating those quantities with the previous time step. So we know the acceleration, velocity, and displacement at the previous time step. Let's take the first one here for the velocity interpolation. We take this middle star here and we relate it to the past velocity step, which was here, and that's logical, and then the past acceleration and the current acceleration. So there's a law now that binds these quantities here together. So I'll make this little boomerang shape. There's an interpolation on displacement here, and that relates this unknown displacement at the current time to the past displacement, and then the past velocity and the two accelerations here. So it does not involve the current velocity, interestingly. Now maybe I can make another boomerang shape here like this one. So this one comes like this, involving these various quantities. And then, of course, the equation of motion itself involved at current time the three quantities. So we have all these relations. Notice that there are some terms that don't appear in each of those relations, and that's what allows the equations ultimately to be uncoupled. And I'll show that in our matrix form in the next figure. It was very helpful for me to assemble the full set of equations, the 3n equations and 3n unknowns, just to see the form of the equations. When I reviewed the original paper by Newmark, this was not done, and I really floundered a bit when all of the scalar ideas were treated. It looked just like magic, but when you do this in a matrix form in the full glory of the 3n equations, you begin to see the pattern here. Notice that the original equation of motion only has these terms m, b, k on the red variables here on the left, and there are no terms on the past time here on the right? Well, that's exactly what the equation of motion is. It's the relation between those variables at an instant of time, a single instant of time. Now, the second equation here is the one that was a velocity interpolation, and we can see that from the gammas that occurred here. They correlate with the earlier equation that we wrote down. Notice that there's a zero here, and that's what's really important. This zero is what helps us uncouple things. And then the displacement interpolation gave the third equation here, and we know that because the betas are entering here, and that came from the displacement interpolation. Again, we have a nice zero here, and it's these two zeros that help uncouple the equations and allow these intricate equations to be handled in somewhat of a scalar form, at least using the submatrices as symbols. Okay, now we will uncouple those equations and solve them as if they were a set of three scalar equations. The third equation, the one that contained beta, was the displacement interpolation, and in it we solve for the acceleration at the current time in terms of the displacement at the current time. But notice there was no velocity at the current time, and so this basically lets us map from displacements to accelerations. So we're going in this direction. The second equation in the set was the one on velocity, and it had a zero in it as well, and we find we can relate the velocities here at the current time to displacements at the current time. And you know what we've done then is we have a way of looking at this other way of inserting every place we see acceleration in the equation of motion, we can put this term on the right. Every place we see a velocity, we can put this term on the right. And we've really reduced the equation of motion to one that involves 3n variables down to one that only involves n variables, namely the displacements at the current time. Let's now see how the equation of motion does change. Here it is in its original glory, and now that we know how to write both u dot and u double dot in terms of u itself, we can just make that substitution. You get all of these terms shown below, and this is an equation that holds at the present time, and it only involves the n variables in the displacement at the present time. So this is n equations and n unknowns and can be solved. The solution is simplified a bit if we define a mechanical impedance term, a little bit like the complex mechanical impedance in the frequency response case, except here this is a real quantity, and it does involve the frequency more in terms of the period of the time step and the period squared. So we'll use this as this new kind of stiffness. It's the K caret here, and when that's put on the left side over here, you have the equation that looks a bit like a linear static problem. In fact, that's the way it's solved, and these quantities from past times on the right side appear like pseudo loads in the problem. So it's a past history now that's catching up and adding into the current live loads. So all this adds with the live load here and gives you the equivalent of a static problem. The coefficients can be found, and it takes about, maybe half an hour to run through all of these equations, and you find these different A values as shown below. Notice that those are the they have different dimensions. Some of them have delta times squared, others delta times, some are just constants. What you're seeing here now is the power of the mass or the inertia effect when you have terms divided by delta t squared. So that at very small times, this inertia term here becomes relatively more important than the velocity or the stiffness. This really reminds me of a case when I was younger. My older brother Albert and I used to read Hugo Gernsback's Science Fiction Plus. And it was a great sci-fi magazine of the late 40s, early 50s. And I still remember the story about the mad scientist who drank this potion that sped time up for him. And boy, one snort of that stuff and he zoomed around like crazy. So the problem was, when he was under the influence of that, he found that normally pliable objects became very rigid because as he ran into them, they resisted greatly. In fact, people became like marble statues. And we realized then at that time that yes, that would happen. If you worked on such a fast time scale flitting around, then the inertia of bodies would not allow you to move them quickly. In one experiment this mad scientist did, he found a person standing in a room and he came up and pushed on that person. And nothing happened, of course, for a period of time, and he held the force on. Then he left the room and zoomed around to other parts of the world. But when he came back, he found that person crashed into the wall. In other words, he put enough momentum into that, or enough impulse into that system, which was a standing human being, to cause a momentum that threw the person violently across the room. And I can imagine the person's chagrin at this, suddenly being from one spot in the middle of the room and then thrown violently to the other side by some unseen hand. The scientist finally got his comeuppance when he was out on a boat on the water, and it was a stormy day, and he saw lightning bolts come around and didn't think much about it until one came after him, and he saw it coming and he jumped out of the boat, and of course he just ran on the water because the water was so hard to displace. It was like solid, and that was his undoing because he couldn't even get under the water. He couldn't avoid the lightning bolt, and it went zig and zag and zorched him right in the seat of the pants, and that was the end of the crazy scientist. But I still did get quite an appreciation what happens if your time scale is such that time is sped up. And that's equivalent to these really incredibly small delta t's that are often used. We have a solution now for displacements at the current time step, and we need to recover the velocity and acceleration information. At first glance you'd say, oh, just take a derivative and that'll give you the velocities and accelerations. But wait a minute, you don't do derivatives in the analytical sense when you're doing numerical integration like this. Rather, you do it by differencing. And really that's what we've been doing all along, is setting up relations at different time steps to try to figure from that what really the velocities and accelerations need to be. Now, as we were uncoupling the equations, we developed two equations that were to help us eliminate velocity and acceleration separately. And now we just return to those, putting in the values of these newfound A coefficients as a help. So we can now recover both the acceleration and the velocity easily. We have a useful integrating formula in our hands that has two arbitrary coefficients, gamma and beta. We might wonder what range of values could gamma and beta take logically. Well, they originally popped up in the interpolating formulas for displacement and velocity. And if you look carefully at that, you see they were a weighting factor that tells how much to emphasize the current acceleration versus the past acceleration. you would think, therefore, these might be numbers somewhere between 0 and 1. I mean, they're not going to be a million or plus a million or minus a million. But let's go into a study on gamma and beta and see what they really should be. We'll consider both accuracy and stability in our discussion. And we'll preview the results so that you have some feeling. Newmark showed that gamma of 1/2 is the only reasonable value. And when you do that, you get very good accuracy, and you do not get the effect of an artificial damping. If you choose another value of gamma, you get something like artificial damping. In structural mechanics, we don't want that. Interestingly, in fluid mechanics, they often do like it because it cuts down on some oscillations when you have flow through shock waves and things like that. But for us, we don't want any artificial damping, thank you. Then beta is actually chosen as a compromise to give both accuracy and stability. It's not the most accurate one, nor is it the most stable that you could choose. And when you take Newmark's two values of 1/2 and 1/4, then you get what's called the Newmark Beta Method. I want to take you through his original arguments by using these defining equations, as Hamming has called them, and we'll see this develop. Our defining equations are an attempt to cause zero error in certain simple polynomial integrations. We will do it as we have done in some other situations where we consider successive polynomial terms in one of the variables, namely in the acceleration. I don't want to work with vector quantities here, so I'm going to consider a system with only one degree of freedom, in other words, a scalar equation. Such a case could be this constant acceleration case of a ball falling in a constant gravitational attraction. So in other words, the acceleration is unity, and we'll assume a unit acceleration, I guess a unit gravity and a unit mass for this body. That falling ball then would lead to a velocity that would be linear in time and a displacement field that would be parabolic. And we'd like to be able to integrate this situation exactly. If you ask where the error has crept into our formulation, it has to be in those interpolating formulas that we used. The equation of motion at the current time was exact, and then we artificially introduced an approximate interpolation for velocity and displacement. So why don't we look at those two equations and then ask that they not be approximate, but that they be exact for some simple forms of integration. So the velocity interpolation formula is shown here. The current velocity depends on the past one, plus this weighted average of the past acceleration and the current acceleration. And you can see gamma here could logically take values from, let's see, from 0 to 1 would make sense. For the given problem, though, of the falling point mass, we know what the analytical expression should be, that the current velocity should be this, and we can calculate then from the various terms above the past velocity and then these interpolated values here of acceleration. Now, since both the past and the current accelerations are unity, things simplify, and when you put the terms in, you get that 0 equals 0. In other words, we identically satisfy the interpolation formula for all gamma when you have a constant acceleration of unity. To some extent, we've just lucked out. We found that whoever set up that gamma parameter did it in a way that it doesn't affect the accuracy of a very simple integration case. Now let's check the choice of beta and see how it affects the interpolation on displacement. Here was the general formula, and then when we take our specific case of unit acceleration that led to an analytical expression for the current displacement, and here was the analytical expression for the previous displacement, then we have to look at the acceleration fields. Now these up here are again just unity in our test problem, and those are put in here and here. When you gather all the terms and turn the crank and simplify, again we get 0 equals 0. So we have really lucked out, and we again have a very accurate answer even for any choice of beta. I think you could see here though, in this case beta might take values from perhaps 0 to 1/2. Would be logical physically, and that would be a way to weight between the current and past accelerations. We're now in the position of a boy who has 2 coins in his pocket, and those are our parameters, gamma and beta, and he has those to spend. And he goes to the candy store and he says, I'm going to start out with the simplest, you know, my old favorite candies, and he asks for the first 2 pieces of candy, and the shopkeeper says, those 2 are free. You have those and you don't have to spend any coins. Wow, what luck. So we're in that same position. But now let's try for something fancier. Let's see about an acceleration that is presumed to be linear. And of course that can be analytically integrated easily. What would be a physical example of this? Well, if you had a rocket that was of constant weight and wasn't burning off propellant, that sounds a little tricky, but its thrust went up like t, or gained linearly in time, then that would be such a typical case. So the force acting on the system is going to cause, for a constant mass, a linear acceleration as shown here. And then the question is, how do our interpolating polynomials fare in this situation? I just heard myself calling the interpolating formulas interpolating polynomials. Well, it's strictly speaking true, but let's call them formulas. So here's our velocity interpolation formula. When we assume linear acceleration, we know how to integrate and get the velocity field here, the current one, and the past velocity field. The accelerations have been directly chosen to be linear in time, so the old one is t0, the new one is t1, and then we just equate terms here. Now t1 and t0 are arbitrary. If possible, we'd like these 3 bracketed quantities to be independently 0, so that we can have this expression true for any starting time and any finishing time in our time step. Luckily, that works out. If you look at each one of those, gamma equals 1/2 satisfies each one, which is more than you could really hope for. So gamma of 1/2 gives you an exact velocity interpolation. Our 4th and last defining equation has to do with interpolating displacements. Again, we assume that the acceleration field varies as t. It's a linear acceleration field. With that, we can integrate and get the current displacement and then the displacement at the previous time step at t0. We put in the this is the past acceleration, and here is the present acceleration. Gather terms, and we again find that we have a series of independent bracketed terms here. We'd like all of those to go to 0, and our luck seems to hold out that beta of 1/6 satisfies all of those and causes 0 error. So if we wanted to emphasize accuracy, and we haven't yet talked about stability, unfortunately, then we would choose beta equals 1/6, and that is called the linear acceleration method. So for an accurate method, that would be the optimum, without considering stability. Well, at this time, we still feel pretty lucky. We're like the boy with the 2 coins in his pocket, and we really got 4 pieces of candy for the price of 2. Unfortunately, we haven't yet looked at stability, and it's a more advanced topic, but I can summarize the results. We've just finished doing what is really the linear acceleration method. That was known before Newmark's time, and of course he was well aware of it. But he did extensive studies of stability of small spring mass systems, and did integration and looked at what happened, and argued correctly that if he could pick beta equal to 1/4, that then the method would be stable. And furthermore, it's been shown since then that that's unconditionally stable. In fact, if you pick gamma to be greater than equal to 1/2 and beta equal to this quantity, and you look at that, you see that the Newmark Beta Method is right on the boundary. It's the most accurate method that still is unconditionally stable. And so that Newmark hit the nail right on the head and picked the very best set of coefficients. I have to give him a lot of credit for working out the stability study. The people who did this more general set of laws were using more powerful mathematics and from general argument, but came along later. So Newmark is rightfully known for having done a really good job on the Newmark Beta Method. We finished with the derivation of the Newmark Beta Method. Now let's compare some implicit integration schemes. We're going to look at the Hubolt method, the Wilson theta method with theta equal to 1.4, and the Newmark Beta method. The test case we'll use is a spring mass system, and we'll numerically integrate what ought to be a harmonic oscillation. The error can show up in several ways. One is that you can have amplitude decay even though there's no real damping in the system. That would be a measure of error. It's shown in this little sketch embedded in the figure. So the amplitude decay might be related to the fractional decay over one cycle of the amplitude of the body. Then the second thing would be period elongation. If there are artificial viscous effects in this, you might slow the system down to where instead of getting the proper period tau, you might get a small amount more, and that's called period elongation. The first figure here shows the percentage of period elongation, and this has to do then with the time step increment compared to the actual period of the spring mass. So as you go to smaller and smaller time steps, you get more and more sample points over the period of the oscillating mass. And of course, as your time steps become very, very small, the error becomes vanishingly small too. If you were to take a certain number of time steps, say 10 per period, then you would come up here and see that the Newmark method gives about 3% error, the Wilson theta about 5, and the Hubolt method about 8. And you can see in this simple problem that the Newmark Beta method would be declared the winner. Remember though that these other methods have been developed a little bit more for random force situations rather than a simple oscillator like this. When it comes to amplitude decay, and that's something in the nature of an artificial damping, the Newmark Beta method comes in with 0 error for all stepping sizes, whereas you do get some error with both the Wilson and the Hubolt methods, namely for 10 samples per cycle, you get 7 and 12%. So it looks as if the Newmark Beta for this kind of work is probably optimum. Let's do a numerical example to exercise our knowledge of the Newmark integration. I've chosen a 2 degree of freedom spring mass damper system. I've picked unit masses here, as you'll see in the data that are given later. I've sized the springs and the dampers to make this be an interesting problem where there's some oscillation under this suddenly applied load shown below. I'm going to take the load on the right mass to be 100 units outboard positive. The other mass will be loaded with 100 units of load negative inboard. When the system comes to rest after some oscillations due to the dampers taking the energy out, you'll find that these two masses have moved apart and the live loads are equilibrated through a force in the spring K2, but the two live loads cancel each other and there's no net force through the spring K1. So you'll see this first mass on the left come to rest after some time exactly at its starting position, whereas the second mass will move outboard. Our goal will be to find the displacements for these two masses by using the Newmark Beta Method. Now the procedure is to solve the Newmark equation using the values gamma of 5/10 and beta of 0.25. I've done this through a small Fortran program and have used subroutines that let me do the decomposition and solve steps that I had developed earlier for a static problem. The main program will set the physical constants, and then the numerical integration is done in the Newmark, or call it the Newmar subroutine. The live loads are given through this force subroutine. So using conventional Fortran programming, you use the artifice of a main program calling on subroutines and then dividing the tasks among those subroutines. I'll show the code in the following figures. The main program of the Fortran code is shown in this figure. Here I set up the dimensions and give the physical constants that I had to adjust until I got the system to be nicely behaving. My time step was 1/10 of a unit. Let's suppose this is in a Newton millimeter second system, and then mass has to be megagram, and then that would be a megagram for each of those masses. Pretty big, metric ton. We're really moving some heavy things. If you prefer to think in English, you can think of foot-pound second system, and then the mass would be a slug, which would be a little more like, 2 bowling balls. That's more reasonable. Anyway, I set the beta and the gamma values here, and then call for the program Newmar to do the actual integration. The subroutine Newmar introduces the constants used in the Newmark Beta Method and does the actual integration. One of the things that's calculated here is the K with the little caret over it. I've called it K hat here. The Newmar program's continued on this figure, and at some point calls for the force, which is calculated in another subroutine. The K hat, which is the matrix of stiffness coefficients, which really involve all of the inertia and the damping and the stiffness forces. K hat has to be decomposed into a triangular factorized matrix, and that's done in the decomp program here. I originally did this for a full matrix for static solution, and it can be used also in small problems for dynamics as we're doing here. The decomposition is a major step in this whole process and by far the most expensive in computational terms. Then once you have that, you solve the problem, and this is all a part of a Gauss elimination set up in matrix form. And the solution then is you have a forward solution and a back substitution, and that's done in this subroutine solve. It's amazing how few Fortran commands it takes to solve even a large set of equations. This subroutine is not developed for a banded set of matrices, and so it's not good for more than probably several hundred equations. I enjoyed programming that small Fortran program, and it helped me run through the Newmark integration so that I got familiar with the various coefficients. I think that for some people it might be worth their while to go through that whole process. I don't really ask people to do much programming anymore in my finite element classes. One thing I do is the Gauss elimination solver in static problems. And this one here on the Newmark integration is the only thing I show people in the dynamic area. But for someone that's a real gunner, you might want to do your own programming. To do the banded version of Gauss elimination on that triangular factorization is a little more work, unfortunately, and that's going to be several days of work, and so I wouldn't do that lightly. And commercial solvers are so much better by now anyway than anything we can hand program that I don't advise that. Alright, here are the results coming out of this program FEMNU. And I plotted separately the displacement on the left mass and the displacement on the right mass. And indeed the two forces tended to first throw the two masses apart by sending the inner mass toward the wall, but only roughly 1.5 units. And here on the outer mass it was thrown outward quite a bit, as much as 10 inches, and then came to rest at a 10-inch displacement. I guess that might make sense if you look at the stiffness and the force involved. It sure looks like 100 units of force pushing against a spring with 10 units of resistance. And everything comes to rest then with the 0 deflection on U1 and this 10-unit deflection on U2. Now we'll have a problem session and have several problems using the Newmark method. Let's start with a spring mass system where it's hanging from the ceiling, but neglect gravity. We're going to assume there's a mass there, a point mass with this mass, and put a force on it. And we're going to say that it has these conditions at time 1.5 seconds. So you've been given both the displacement and the velocity. And then the question is, what would be the position at the next time step of 1.51 seconds? So it would be a 100th of a second time step carrying it forward. Now, it is interesting to think then whether it's primarily the mass or the stiffness that will govern that motion. And if the time step is small enough, we know that the inertia terms are pretty big. We'll pick the standard Newmark values of gamma equals 1/2 and beta equals 1/4. The integration formula, when there's no damping, which is our case, is like this. And we have all the required quantities except for acceleration at the starting time of 1.5 seconds. And that's needed, let's see, at this point here. That can be found from the equation of motion, and substituting in the numbers we get that. So I've just used the equation of motion itself to fill in one missing piece, and see that there's quite a large acceleration here. A second important calculation is that for the k hat, and that's quickly found as 50 newtons per millimeter. So this is the effective stiffness. Then we go back to the integration formula, putting that number in where it belongs, and adding other things such as that acceleration where it belonged, and you pick up the current position of the body at 8.57 millimeters. Now it was starting out in our first calculation at 1.5 millimeters, so it has moved a distance of roughly 7 millimeters in a hundredth of a second. Now I'd like to pose one of the simplest structural dynamic problems that you could pose to be solved with Newmark Beta Method. Here's a beam that's clamped at the left end and guided at the right. That means there is no slope at the right end nor any shear force. So it's a roller skate condition. There's a 10,000 Newton vertical load applied there at time 0. We're going to study this system and find the response using one element and Newmark Beta Method with 100-second time steps. There's no damping in the system, and you're given the results at a time 1.05 seconds, and we're going to be asked what is the solution at 1.06 second, a hundredth of a second later. Next, I give the material properties and the geometric properties. And here's a statement requesting the displacement at the tip at 1.06 seconds. This problem's a lot like the last one, and these appear as exam questions typically in my course, and so that's why they've appeared here in the problem session. So you can pretend you're under the pressure of a time deadline to do this in 20 minutes. Setting up the structural dynamic problem is kind of fun. You take one beam element, one Euler-Bernoulli beam element, since this is a slender beam, and then constrain the accelerations here at the root, and then the rotational degree of freedom at the right end. And after crossing out rows and columns, you end up with a scalar equation with only one unknown. We then go into the Newmark equation to be solved, and here it is for the single variable u3 at t plus delta t. Then I do some calculations for the structural mass and stiffness coefficients, and then we have to find the Newmark beta quantities, the a's shown here and on the start of the next figure. After finding these remaining coefficients, we can solve the problem, and we take one further time step, bringing us to 1.06 seconds. Putting in all those terms, we find that the displacement is 2.93 millimeters. Now it had started out at 2.73 earlier, and so it's moved 2/10 of a millimeter in 100th of a second. So I guess you could even calculate a velocity just by that simple differencing. Or you can go in and really use the formula that you're supposed to use. Our final problem is to set up sort of an academic situation where we want to exactly integrate a process that has an acceleration field defined by a constant and a quadratic acceleration. It's vaguely possible to have such situations where you have perhaps a quadratic spring, say, or some force field which would tend to give you such an acceleration field. But it's a little bit far-fetched because this would be a special purpose Newmark Beta integration. So the idea is that we want to find the conditions that gamma and beta hopefully would have to give zero error in the velocity and displacement interpolation. And is it possible to develop such a special Newmark Beta method? So the idea is to look to the defining equations and see what we get. Well, we've already proven that the general Newmark scheme is identically satisfied for constant acceleration. We've been told that we don't need to worry about linear acceleration because it won't happen. So therefore we advance to quadratic acceleration terms and see if we can satisfy those when we're dealing first of all with the velocity interpolation. So this quadratic acceleration term t squared can be analytically integrated to give velocities and displacements. We look at the velocity interpolation formula, and that's the one that involves gamma. We put in this quadratic case up above, for instance giving these acceleration terms t0 squared and t1 squared. And then we equate these various terms and see if it can be done. So we multiply out and simplify, and then we collect terms on the different coefficients here, and we find that we get contrary requirements here. So there's no way for arbitrary t0 and t1 to satisfy all of these. Now, I'm not completely happy with this solution because the only true variable here is t1 minus t0 over that range, and I would really rather cast this set of terms into only two terms that multiply t1 minus t0 perhaps to the first, second, and third power if it so happens. Now you might still get four of them, but certainly we see that it's not easy to figure a solution to this set of equations. I'm not certain if this is the only proper, I don't know that this is a necessary and sufficient set of equations is what I'm saying, but it was kind of fun just to look at this as first cut. If some real smart person in the audience wants to try this in a little different form, that would be great. I'm pretty sure though you're going to find that quadratic acceleration is going to be very difficult to satisfy even adjusting both gamma and beta.